So it's time to start. So I'm very happy to introduce the talk of Leo Gross from IBM, who will talking about on-surface reactions and single molecule charge transitions. So please, Leo.
Sydney, thank you. Thank you for inviting me. It's a great pleasure to speak here in Israel today. Okay, so I'll show you a lot of work in a 20-minute talk. So I'll keep the introduction short, but let me introduce you the most important people to you that actually did this work. This is Shadi Fataye, Katharina Kaiser, Florian Albrecht. Okay. This is a short outline, so I will very briefly introduce you to our techniques, STM and AFM, and then I'll very briefly show you how you can use it for structure elucidation. And then the main parts, I'll show you how we can do chemistry using the tip of our microscope and how we can control charge states on molecules and what we can learn by that. Okay, so that's the introduction to the technique. So I just want to mention all experiments are done at 5 Kelvin in an ultra high vacuum system. And we use sensors that can be used to both measure the tunneling current for STM, scanning tunneling microscopy, and the force for AFM, atomic force microscopy. And these are these Q+ sensors as proposed by Franz Giesibel. So they oscillate and we record the frequency shift, and this gives us information about the force. And then we have, in the end, we have a tip. We use a focused ion beam to first cut off our tip and shape it roughly. And then the most important step probably, and this is really what gives you the high resolution, is to pick up dedicated atoms or molecules to functionalize your tip. And what we use a lot are CO molecules for tip functionalization. So here you see two CO molecules on the surface. And when we pick one up, you see the other one has somewhat changed in appearance. And now the tip that we have, so there's a lot of background noise, would be great. Thanks, much better. So that you can imagine the tip then to look like that. So we have a metal tip. This is just a comic, but what we know is that in the end, to our last metal atom, we have the carbon atom of the CO, and then the oxygen points forward. And now if we use that tip, then we actually get this high resolution images. So here you use, that's the AFM signal, and you see the frequency shift, and you see bright regions due to Pauli repulsion above regions of high electron density. And so you see the bonds and the atoms in these molecules. I don't want to go in big detail here. What's important to keep in mind that with AFM, you're sensitive to the overall electron density via Pauli repulsion. No, and so AFM then gives you information about the structure of a molecule, as you've just seen. So this is always the same molecule, naphthalocyanine. And this is just to showcase how the different microscopy methods give you complementary information. So with scanning tunneling microscopy, you can access the orbital densities, so the frontier orbitals, by selecting whether you resonantly tunnel in or out of the molecule. You see the LUMO or the HOMO, and you can image those. By AFM, you see the overall electron density, and you get information about this geometry and also bond order, as we will see later. A third method is Kelvin probe force microscopy. So this is now AFM as a function of voltage, and it gives you information about the net charges in the molecule and the electric field above the molecule. That's pretty much what you image with that. Okay, that's it already for the introduction. Now to the applications. So what can we do with it besides taking nice images? So very straightforward, we can identify molecules. So we can just take an image and then we might learn which molecule that is. And here we did that on a metabolite from the deep sea, and we can actually get out the structure of this molecule. This is now really a niche application, and NMR and mass spectrometry are the gold standards to find out the structure of a pure compound. However, there's one big advantage now in scanning probe, and that's the single molecule sensitivity. So if you do not have a pure compound, but you have a mixture of molecules, now AFM is great because you can study that mixture molecule by molecule. And here we could apply our tool to do it that way in different fields. I don't want to go into detail, but I just want to show you in which fields you find these planar aromatic molecules that we can image nicely, and you can now learn something by studying individual molecules out of these complex mixtures. And these are complex mixtures that are interesting around petroleum industry, so crude oil and oil and gas production. So these are molecules we find here. These are also molecules that are very important in incipient soot formation. So like this fine dust that forms in exhausts. And here we can study the single molecules that form larger soot particles. Or marine dissolved organic carbon, or this year we studied actually lab analogs of molecules that are supposed to be in this atmosphere of Titan, a moon around Saturn. Okay, so this is exploiting the single molecule sensitivity of AFM. Now there's another thing that we think that is great about our technique and that we like a lot, and that is atom manipulation. So by applying voltage pulses, we can actually do chemistry with the tip. So we can change something. And this is what I want to show some examples next. Okay, we don't want to make like huge amount of molecules and produce them, but what we can do is we can try to make molecules that are very hard and challenging to make otherwise. And since we work at low temperature and sometimes also on very inert surfaces, we can make molecules and characterize them that are unstable under other conditions. And one prominent example that we did is this triangulene. So that's this molecule, and Clar and Stewart, so from the Clar-Sixtet rule, he'd already tried to make that a long time ago, but he didn't succeed. The problem is this molecule is too reactive. No? It is an open shell molecule with presumably a triplet ground state due to different A and B lattice sites in this small graphene flake. And this was not possible to make. And on the surface, we can make this by atom manipulation. In this case, we dissociated hydrogen atoms. No? So we have this precursors and we take away the hydrogen atoms and we form triangulene. By now, other molecules have also been formed. And you can, in our case, we did this by atom manipulation. These other molecules were done by on-surface heating. So you also put precursors, but then you form bonds and dissociate hydrogen by heating it up. For this molecule, both methods work. For the next one, this is even more reactive. And here only the atom manipulation route would work because you cannot do this one on a metal. So here the goal is to make cyclocarbons. So that's the allotrope of carbon. It's a very elusive one. It hadn't been investigated before or couldn't be investigated because it's so reactive. And actually theory was also very unsure what's the correct structure of this molecule. So let's think about a molecule that has 18 carbon atoms arranged in a ring. So there's no hydrogen in this molecule. And now you can come up with two different resonance structures. You can either draw alternating single and triple bonds or everything as double bonds. And theory, every 2 years, another paper came out that contradicted the view before and either found the cumulonic or then again the polyionic structure. So it wasn't clear. And this molecule now we made again from a precursor. In this case, the precursor came from Laurel Scriven from Harry Anderson's group of Oxford. And this precursor holds these CO molecules at the edges. So it's kind of a triangle. And here you see again an AFM image. By the way, you see again already this bond order differentiation. So you see these triple bonds due to their larger electron density, they appear brighter in the images than the single bonds. And then on the CO groups, actually you have little repulsive contrast. And now this experiment is done on a double layer of salt on a copper surface, which is very inert. So here you can make very reactive molecules and they will not form bonds to the substrate. And now by voltage pulses, Katharina Kaiser did this experiment. She dissociated these CO groups. And you form now here this 5 consecutive triple bonds that you also see, and you go on with that, and you go on, and finally you dissociate all the COs, and you come up with this cyclo-18 carbon. And now you can compare the structure to simulations, presuming it would be either polyionic or cumulonic. And what you see is if you calculate the cumulonic form, this molecule would look very much like a ring. You have 18 equivalent bonds, whereas this polyion at a large tip sample distance, you would see 9 maxima. So this you see here in the simulation, corresponding to the 9 triple bonds and their higher electron density. And this is what you see in the AFM image. And now when we go closer with the imaging plane, and now we have the CO molecule again at the end of the tip, remember that? And if we go closer now, this CO is not very stiff. So now its tilting will play an important role in the image contrast. And this causes then to that you come up with an image that has now 9 corners. And now the 9 corners are at the position of the triple bonds. And this is also predicted by theory if you assume the polyionic ground state, and only then. So here we can really now find out the structure of this molecule, at least on salt. It's in the polyionic form, so with alternating single and triple bonds. We found the molecule also interesting as it allows us to also do further on surface reactions. I told you, you cannot make the molecule that's so very reactive, but we can also exploit this reactivity in the plane if we bring precursors close together. And this we did here. So here we have 2 of these precursors. So some of the masking groups have already been dissociated in these 2. And now by applying 3 volts above them, we actually fuse them and form this ring between them, and have now fused these 2 carbons. So this might be useful to make other carbon-rich and design structures. And on the second slide, on the right side of the slide, I show another precursor with bromine. So this was nice. Here we can increase the yield to make this cyclocarbon by atom manipulation by a factor of 4. And we also did some deeper analysis of the structure of this polyionic cyclocarbon. All right. This brings me to the last part of the talk. So now we will also play with charges. And to do that, we go a little bit on a different substrate. So now we work on a thicker insulating film, and the film is so thick that you cannot tunnel through it. So now you can only exchange charges between the tip and the molecule. Before, it was possible to tunnel between tip and molecule, and to tunnel again between through a double layer of salt to the substrate. But now the film is more than 12 monolayers, so there will be no exchange of charges with the substrate below. First thing is, this allows us to charge molecules, and the charge will stay on the molecule. This we show here. We have 4 molecules on this thick film, and we can deliberately charge them. In the beginning, they were all neutral, and now step by step, we charge them either attaching or removing an electron. Here in the final image, 2 of the molecules are charged positive, and the others 2 are charged negative. The contrast is very bad here, because to not take these charges away with the tip, we have to stay very far away with the tip, and we only measure very weak electrostatic interactions here at a very far distance. But that's enough to infer the charge state. We can combine now this high resolution imaging with this charge state control. If we actually go close and we still apply a certain voltage, we trap the molecule in a certain charge state. So here we see that on pentacene, we take this parabola corresponding to the Kelvin probe force microscopy, and then we see certain transitions to a different parabola, and these correspond to charge state transitions. So this is done on pentacene, and here on pentacene, we can image it in the positive, neutral, negative, and doubly negative charge state. And now we can do that, and now we can again take at this voltage, at this charge state, an image with our CO tip. I just showed this one example here. We did this on a couple of molecules, but maybe the porphine is the nicest, and it's also a very interesting molecule in terms of biology, because it's a parent compound of hemoglobin or chlorophyll, with important charge state transitions in life and nature. And here we can image it in the neutral, negative, and doubly negative form. And you see faint differences in the molecular structure and in the apparent bond length. So for example, you see that this bond is apparent length is short in the neutral charge state, and it gets larger in the doubly negative one. And you can understand this very simple in these resonance structures. If you look here for the resonance structures for the neutral molecule, you see it's a double bond in all resonance structures. So therefore it appears short. Again, this is an effect of a CO tilting. Bonds with a strong bond order appear shorter. And we see that effect. But now if it's doubly negative charged, it can be, its bond order is 1.5. No? It's a single bond once and double bond once, so its appearance gets longer. And you see other effects also at the methane bridges. Okay, due to time, I want to go quickly on a little bit and just show you that you can also do spectroscopy with the AFM. So here we now exchange single electrons. And when doing that, we can now measure charge transitions that you cannot measure with conventional tunneling spectroscopy using the STM. So we do not measure a current through the molecule yet, but we just attach electrons and then at different voltages take them away with a tip again. And by that, we can measure transitions that are inaccessible otherwise. First, we show that we can basically go back and forth and measure charge transitions going to positive and going back to neutral. And with that, we get the reorganization energy. Due to time reason, I do not show the concept here, but just short, this is based on measuring the time of single electron charging events. So you sit somewhere with a tip and you wait 10 seconds and you see when is a single electron tunneling. And then to account for statistics, you have to do that many times. But if you do that, then you get in the end spectra. And these spectra are with zeptoampere resolution, just because it's based on single electrons. And you can now measure these different charge transitions. So that's a charge transition you could measure with STM, but the reverse one, going back from the charge to the neutral, you could not. And their difference actually tells us the reorganization energy. And we can play this game further. We can now even measure transitions to excited states. So here we measure transition to the neutral ground state, or to the triplet excited state, or to the first singlet excited state of a neutral molecule. And we can measure those energies as well. And so this is now really the last thing, and then I'm going to quit. This has been automated. So this is a group of Yasha Reps, a work of Yasha Reps group by Jingbo Peng as first author. And he showed, and he automated this, and he showed that you can measure triplet lifetimes of individual molecules with that approach. And the really cool thing is now, and so basically that's automating it in a pump probe scheme and doing all these transitions many times, and then basically measuring average forces in the end, so with the AFM. And the cool thing is now, of course, you have that combined with the atomic resolution, so you can investigate triplet quenching by molecular oxygen, and you actually see how the position and the amount of oxygen molecules next to the pentacene triplet state that you quench affect the quenching of the triplet state and affect the lifetime of the triplet state. And you see it's really huge differences depending on where that oxygen molecule sits in the lifetime of the triplet state. With this, I'm going to finish. Small summary of the final part with the charge state. I showed you that we can control charge states. We can obtain atomic resolution and bond order analysis in different charge states. And we can use the AFM for tunneling spectroscopy. And with that, we measured the reorganization energy. We measured excited states in spectroscopy, and Yasha Rep's group measured triplet lifetimes with that. I thank my group. Katharina Kaiser, she was the most important work doing the cyclocarbon. Shadi Fatayer and Florian Albrecht, and in particular, Shadi was the most important work for this last part, this work on the thick insulating films. And I like for my funding sources to thank them, and I like to thank you for listening to the talk. Yeah, and hope for
Okay,
some
great.
questions.
Thanks a lot, Leo. It's a really fascinating and beautiful talk. We have time for only one very short question. If someone wants to speak up, otherwise I do have a question.
I do have a question.
Yeah, okay, Odette, go ahead.
Exactly two. I hope they will be quick. First of all, you measure the scanning Kelvin for microscopy. Can you measure in parallel also EFM? Because if you're talking about charging, they're related to one another, but not necessarily exactly the same. And second, you had this telegraphic noise at one of the end slides. Did you study the statistic of that? It's parallel or has it? Yeah, this one. Does it have a parallel behavior, the on and off times?
Okay, so the first one, I mean, that's what I think was the question was between KPFM and EFM.
Yeah.
So we only do, I mean, you can call it both ways. What we do is we record parabolas and then we determine the peak position. And this is very similar to KPFM, but it's also very similar to EFM. And I don't want to have a discussion about this small, whether they're the same or what their difference is. So we do that.
I think we'll have to cut it at that. I'm very sorry. And maybe, Leo, you can write the answer in the chat because we already over time. We need to move on.
I was too long, 2 minutes.
So can you please remove your thing and then Martin?
Okay.
So great. We're off to a good start. Our next speaker is Martin Castell from Oxford, who will be speaking about multiple frame averaging of scanning tunneling microscope images.
I hope you can hear me okay.
Yeah, we hear you fine. Yeah.
So I'm going to go and share screen now.
So I guess I will give you, Martin, the 2-minute warning before the 3-minute question thing, just so we make sure we keep on the time. Are you having troubles getting your screen up?
I pressed share screen.
Yeah.
And it's making me open system preferences.
You should have no trouble to put up. You should be able, anyone should be able to share a screen.
Yeah, I'm having difficulty with this.
Only thing I can think, if you can't do it, if you want to quickly send it to me by email and I can put it up.
Yes, I mean, I've had this issue before. I don't quite understand why open security and privacy to grant access. So I need to go to security and privacy, but I'm actually on that, and everything should be okay. So,
but you maybe should press share. Yeah.
Yeah. So I've got share screen.
Yeah. Yeah.
And then I'm pressing share.
Yeah. The security settings for the Zoom are that any participant can share a screen.
Yeah. Well, that's not working from my side though.
So can you quickly send it to me and I will put it up? And I'm just wondering, in the meantime, maybe the best thing to do is to start the first invited talk, which is Nurit Abraham.
Yeah, I'm here. Yeah. You want me?
Yeah,
you want me
please go ahead, and then we'll do Martin right after that. Yeah.
Okay.
So it's Nurit from the Weizmann will be speaking about visualization of topological boundary modes manifesting topological nodal point superconductivity. Great. Okay.
Wait, so let's see if you see my. Okay, you see my screen?
Yes. Yes.
You hear me well?
Yes. Go ahead.
Okay. So. Wait. So thank you, Sydney, for the introduction. So today I'm going to tell you about scanning tunneling microscopy measurement we've been doing on the transition metal dichalcogenide 4Hb tantalum disulfide. More precisely, I'll show you visualization, STM visualization of boundary modes that manifest the existence of topological nodal point superconductivity on the 1H termination of the material. So before I start, let me introduce the people that were involved in this work. Abai Kumar Nayak, I'd like to specially specify Abai Kumar Nayak, our former PhD student, now in UCSP, that did fantastic work, both in taking the measurement and analyzing them, together with Aviram Steinbock, Yotam Roth, Bin Gayan, Jun Ku, Omri Lesser, Gilad Margalit, Yuval Oreg. This is from the Weizmann Institute. Irena Feldman, Avior Al-Mualem, and Amit Kanigel provided the sample and a lot of wonderful, great discussion. Gregory Fitt and Chaim Beidenkopf, of course, from the Weizmann. So a few general words on topological superconductors. So in general, topological materials are materials that exhibit unique topological surface states on their material surfaces and boundaries. And these states exhibit unique properties, and they cannot be realized as standalone systems, but only when they are coupled to some topological bulk. So topological superconductors are such topological state of matter. They exhibit such unique topological states that are called Majorana states. Now, these Majorana states are particularly attractive since they provide method for storing and manipulating quantum information, and therefore topological superconductors are promising candidates for the development of quantum computation. Now, previous studies found topological evidence for topological superconductivity mostly in heterostructures and hybrid systems, but finding it in intrinsic material is relatively rare. So here I'm showing you evidence for topological superconductivity in the TMD 4Hb tantalum disulfide.
I knew
Okay.
it. You are,
Yeah.
I think, in the wrong mode. Can you swap screens? Otherwise, we see your preview.
So,
Yeah, thanks.
okay, but I want to. So, but then I need to. I'm not looking to.
It's good now.
No, wait,
Okay,
it is
but
okay
now-
now. It is okay now.
Okay, so I need to look on this screen. Anyway, okay, I'll do it here. But then I'm not doing it. So, okay, so the outline will be as follows. I'll start with an introduction about 4Hb, and then I'll talk about the two polytypes that consist this layered compound, and then I'll present the superconductivity that exists on the surface, and then I'll show you evidence for the visualization of the edge modes that are the signature for the topological classification of this superconductivity, and probably I won't have time to go to the theoretical model that capture all this phenomenology in a model for multi-orbital topological superconductivity in the 4Hb, but you will be able to read about it in these two papers that were, one of them were just published 1 week ago. I cannot. Okay, so let me start with the crystal structure of this 4Hb tantalum disulfide. It's just an alternating stacking of the 1H and the 1T polytypes of tantalum disulfide. The difference between the 1T, structurally, the difference between the 1T and the 1H is that every layer is consisting of a layer of the transition metal, encapsulated between layers of sulfur. Now, in the 1H, the two layers of the sulfur are aligned vertically, one with respect to another, whereas in the 1T, the two sulfur layers are twisted by 60 degrees, one with respect to another, and this is, you can see this clearly in the top view of the different layers. Now, okay, so both like the 1T and the 2H, which is the bulk form of the 1H, both were studied extensively, and they both show a lot of phenomenology, and they are interesting even before stacking them in the 4HB. So let me present some of the phenomenology that was found for the 1T and the 1H. So in the 1T, in the bulk, it was reported that CDW are formed on the surface. These 13 by 13 CDW in the form of Star of David, when 13 atoms are bunched together to form this Star of David form. As for the spectrum, it was attributed to a Mott insulating phase. And since this is a triangular lattice of charge density wave with localized spin 1/2, it was suggested theoretically that the ground state of the system will be a quasi-spin liquid. And recently there were evidence for experimental evidence for this ground state, and also signature for Wigner crystal on domain walls in this CDW formation have been reported. As for the 2H, the 1H also has its own CDW structure, which is different from the CDW structure that we have on the 1T. It is the 3x3 CDW. It is a superconductor in its bulk form. The TC is around 0.7 Kelvin. In the 2D form, the TC grows to around 3 Kelvin. Due to strong spin-orbit coupling, it is known for its Ising superconductivity. Now, the 1T, the 4HB is an alternating stacking of these two strongly correlated states. And recently, it became also a subject of experimental studies. It was found to show Kondo lattice, a Mott collapse, since the 1H kind of suppressed the interlayer coupling between two 1T layer, and then we move from a Mott insulator to this state where we have a flat band just above the Fermi. And also experiment of muon relaxation have found an increase in muon relaxation that onset together with the superconductivity, suggesting a time reversal symmetry broken, which suggests that this the superconductivity is actually a topological time reversal symmetry broken superconductivity. And this is the work that actually motivated us to study this using STM. So in STM, we bring an atomically sharp tip to close proximity with the sample surface, and we measure the tunneling current between the tip and the sample. So here is a single crystal of the 4HP tantalum disulfide. We cleave it, expose pristine and clean surfaces, and we measure. These are a typical topography that we get, and we can also measure the DIDV, the derivative of the current with respect to the bias voltage, which give us the local density of state on the sample surface. So here we see we found all possible configuration when the 1T is below the 1H. Here we have the 1H below the 1T. We have craters. We are different kinds of steppages configuration on the surfaces. So now let's see the electronic properties of the different surfaces. We will concentrate on the 1H. We have other work on the 1T, but now I'm focusing only on the properties of the 1H. So this is the 1H. These are vortices that are on the 1H. So let's see what are the properties. So here we see again the topography. The 1H is above the 1T. So what we see here are the CDW, not the crystal structure. If we take a zoom, we see here a magnified topo of this region, and we can clearly see the Star of David, and behind it we see the crystal structure. If we take a Fourier transform, we see the Bragg peak that correspond to the crystal structure, and we see the Bragg peaks that corresponds to the CDW formation. If you go to the 1H, we see a CDW formation, which is very similar to what we see on the 1T. And this is not by chance, since what we see here is an imprint of the CDW that we have on the 1T. We see an imprint of it on the 1H due to its proximity to the 1T. In addition to the 3x3 CDW that the 1H has on its own. So here we see the crystal structure Bragg peak. And here we see two Bragg peaks. The faint one is the one of the 3x3 CDW corresponding to the 1H, and these one are the ones that are imprinted by the 1T, showing the interaction between the 1H and the 1T. Now let's see the spectrum on the two different layers. So this is the 1H spectrum in its normal state. We see a metallic spectrum, and this is the 1T, which is almost insulating below the Fermi energy, and we have this increase of density of state just above the Fermi energy. So now let's cool the system to about 0.4 Kelvin, and we see a very nice superconductivity gap. Note that the density of state doesn't go all the way to zero at zero bias. We have some residual density of state at zero bias voltage.
Nuri, just a 2 minute,
yeah.
2 minute warning. Okay, so try to finish in 2 minutes, okay?
No, I can't finish it in 2 minutes. So, okay, when we increase the field, when we increase the temperature, we see the disappearance of the superconductivity. So now let me go to show you. So this superconductivity is uniform on the surface. So let me go and show you the one-dimensional channels close to the edge, which are the most important. I'll skip these vortices and the zero bias peak that we see in the center of the vortices. So this is the topography, this is the 1H and this is the 1T. And if we take the IDV, you see an increase of the density of state just close to the edge. And when we apply magnetic field, this disappears, meaning that this channel appears only in the superconducting form. And if we take a line cut and we see how this channel develops when we go from inside the terrace to the edge, we see that the density of state increases already here as a function of position. This is the IDV along this line. We see an increase of density of state close to the channel. However, the gap, the superconducting gap measured by the distance between the coherence peak and this zero bias, we see that it remains constant almost till the last end. So this means that this increase in the density of state doesn't come from suppression of the superconductivity, but rather it's an additional density of state that comes from this one-dimensional channel that resides close to the edge. So I'll skip this and I want to show you another kind of one-dimensional channel. So right now I describe this channel along here between the topological superconductivity and the vacuum. I want to show you another one-dimensional channel that resides here between a region which is encapsulated by 1T from both sides and a region which is exposed and is encapsulated by 1T only from below. So this is the 1H, this is the 1T above. And here you see this one-dimensional channel running along the 1T steppage. And the way we understand it also, okay, so if we concentrate here, we also see that this one-dimensional channel is anisotropic. The localization length along this boundary is much smaller than the localization length along this, showing that there is some anisotropy in the formation of this one-dimensional channel, which can be explained by the model for the nodal point superconductivity that we developed.
Yeah, sorry, Nuri, you have less than 1 minute to wrap up, so try to wrap it up now. Okay. I'm sorry, we have to keep on schedule. Yeah. Okay, so the one last thing I want to say about this is that what we found is that when we, due to the proximity to the 1T below, here we have, from DFT calculation, we found that there is a charge transfer between the 1T to the 1H, and when it happens from both sides, it remains symmetric and there is no net polarization. However, here there is charge transferring only from below, and this leads to mirror symmetry breaking, and this enables the formation
of topological superconductivity. So this channel that we see here is the channel that distinguishes region of topological superconductivity and region with trivial superconductivity on this region that are encapsulated. So we see these two visualizations of one-dimensional channel.
Nurit, your time is up. I'm sorry. I'm really sorry to the speakers, but I also have to go to host the next session, so we have to be very quick about time here. Please write any questions you have in the chat to Nurit. In the meantime, can you unshare? And Martin is going to give it another try now. Ah, very good. Okay, so again, we've got here Martin Castell from Oxford, who's going to be talking about multiple frame averaging of scanning tunneling microscope images. Please, Martin.
Can you hear me okay?
Yes, we hear you fine.
Great, that's excellent. Sorry for that earlier problem. So I will talk to you about multiple frame averaging, and in STM images, the people involved with this were Lewis Jones, who's now at Trinity College Dublin, Shukui Wang, who's now in the physics department in Oxford, and Shams Raman, who's in Pakistan. So I will talk to you about this today, and I will start off by showing you it's actually a simulated XPS spectrum, but this is a sort of XPS spectrum you might take, and it's rather noisy. And if you try to convince yourself, you might say, well, there's a peak in here. So what do you do if you have a noisy XPS spectrum? You take lots of them. So if we have 9 different XPS spectra and we average all of these are all different, then we get this one here, right? So this red one is the averaged SPX spectrum from all of these 9 here. So the noise is reduced as a function of the root of the number of scans. So we get an increase in the signal to noise ratio of a factor of 3. So we can do this, of course, multiple times. So I'm going to average 100 XPS spectra now, and the result that we get is a really clean averaged scan. So we go from something, the blue one here where you can barely see anything, to the red one where you can see very clearly there are even multiple peaks in here. Okay, so you're thinking to yourself, just a minute, I know all about this. This is not news to me. I know that if I average things, then I can increase the signal to noise. But you do not do that with your STM images. What you do with your STM images is you take the best one and you call it the typical image, and you throw all the others away. So what might happen if you average lots of STM images? Well, I've lined them all up here, and I'm going to average 66 images. And let's see what happens. So here are 66 images. I've lined them all up, top left-hand corner, and I've done it to the best of my ability, and I've done that by hand. And the result that I get is this. So where I've lined them up by hand, they look pretty good. But down here, that's clearly no longer a representative of the structure that I had here, which was a honeycomb structure. And this is due to small image distortions. The atoms don't line up, so only the top left part of the corner is actually a properly enhanced image. So what can I do? Well, I can use something where I use automated aligning. And if I use automated aligning, then I make sure that all of these images are really well aligned, the image distortions are removed, and then when I average those, I get a vastly increased signal to noise ratio. You can see in this image, we can see the atoms really well. These are titanium atoms. You can't see the oxygens in between, but you can see the titanium atoms much more clearly than you could ever see in this rather noisy image. And that's purely due to image averaging. So how can you get the most out of your STM? Well, like I said before, if you're an STM operator, you normally take multiple images and you throw a lot of those away. But what you can do, if you're an XPS, if you take an XPS spectrum, you take lots of images and you average them. And why don't we do that for STM images? Well, the reason is because of these image distortions, and they mean that it's much harder to align images than it is spectra. But we do now have automated software packages that were originally developed for scanning transmission electron microscope images, and they're commercially available. One of them is described here. and you can use those. And we have adopted this one. It's called Smarter Line, and we adapted it so that you can use it for STM images. So you substantially increase your signal to noise ratio as a function of the root of the number of images that you take. So I'm going to show you some examples. This is a familiar silicon 111 7x7 reconstruction. Top left is a single noisy image, and top right is 41 images average here. So we've averaged 41 images here. You can see the signal to noise is improved. And if we look at this small region here, from both of those, you can see the noisy image here has been vastly improved compared to the much smoother image when we've averaged 41. And let's have a look at the statistics of that. Well, if we have the number of summed frames here, and we use something called the noise power, which is a slightly odd way of describing it, but it's basically just the amount of noise we have in the image. You can see as we average the number of images, then the amount of noise in the images comes down and down and down. You can see after 10, you've really done a pretty good job already, but this should in theory be minus 0.5 because it should go as the root. This red line should go as the root of the number of images. It's not quite that, but that's because of the nature of how you measure the noise, and that's a subject in itself. Of course, what you can also do is, let's go back to this, if you have a single image, you can just select lots of bits of the single image, and atoms being the same wherever they are on the surface, as long as the reconstruction is perfect, you could average this unit with this unit here. So you can take single images and you can do unit cell averaging. So again, you can vastly increase your signal to noise. So this is from 9 average tiles, and this is from 27 average tiles. And it would be very difficult for you to get an STM image from a single scan where you had signal to noise that was of this quality. So that's for the filled and the unfilled. People will be familiar with this, and this is the enhanced image for both of those. Now, we've done a lot of work on strontium titanate. This is the 111 surface. There's a 4x4 reconstruction, and you get images like this. This is the 4x4 unit cell. 4x4 reconstruction is very interesting because it has something called a chiral reconstruction. If you look at this unit cell here, then it doesn't have mirror symmetry along the middle. If you compare it with this unit cell here, then there's a sort of a chiral. This, you can imagine these rotating to the right. You can imagine these rotating to the left. And if you take lots of these here, we've done 297 images that we've averaged. So we get this really clean image. And here we've done 15. And you can then get the computer to find for you the individual regions where you have these chiral units. So you can see the domains of one chirality versus the other. And we also have improved image rendering. So this is some work we did at quite high temperatures. So this is almost 800 Kelvin. And this is, these are the so-called nano lines on strontium titanate 001. And these are just the images put on top of each other. But if you use this image package, then you can remove all of the backgrounds. You can ensure that everything is lined up very well. And that means that you can then see individual defects like this. You can see there's this double defect, and that's diffusing up and down the line here. There's another one diffusing along here. So that's at 800 Kelvin. We can do that because the signal to noise now is much enhanced. So I'll go on to now to discuss a little bit what we've done with these 2x2 TO203 honeycomb structures. This is a gold surface here in yellow. That's the top surface. And we put titanium atoms here. The titanium atoms sit in these threefold hollow sites. And then the oxygen atoms sit in between the titanium atoms. And that gives rise to this honeycomb structure. And that's been observed we've observed it for TO203 on gold, but you can see it for vanadium on palladium or on platinum or on niobium oxide on gold as well. And if you do lots of image averaging, then you see the titanium atoms really well. And this is the structure. And this is the DFT simulation, so that pretty much fits in with what we've seen. This is that 88 images averaged. So here we have a raw image. This is the raw honeycomb image. If we average 528 of these, then you see the titanium atoms much better now. In fact, you could barely see them here. What you can also see, if you take a scan across here in the raw and the highly averaged image, in the raw image, you just get lots of noise. But here in the processed images, you can see there's a difference here between these, what we call the A sites and the B sites. And if we vastly enhance the image contrast, then you can see that half of these sites are slightly brighter than the other half. In this image, you can't quite see it, but if you really enhance the contrast and use false color imaging, you can see that these three sites are these, what we call A sites, are brighter than these B sites. And they are brighter by just over a picometer. And we can look at the difference in the brightness between the A sites and the B sites, and that's of the order of a picometer, just a little higher. And the spread of those measurements is of the order of about a quarter of a picometer. So what we're doing now is we're looking at image height differences to a precision of better than a picometer. So that means that we can look at things that we previously were not able to see. Now, what's the origin of the difference between these A sites and the B sites? Well, here's in the background, I've got my gold surface, and these blue atoms are the titanium atoms sitting in the threefold hollow sites. The red ones are the oxygen. If we just move over to this part, I've removed the oxygen now. And if we move over to this part, we can see that the blue atoms actually sit on the FCC sites, and these slightly lighter, so the dark blue ones, the lighter blue ones sit on the HCP sites, and the HCP atoms appear slightly higher than the FCC ones by around about a picometer, and DFT confirms that. So the only way we'll be able to see the only way we would ever be able to see those differences is by using this multiple frame averaging to get these incredibly high signal to noise ratio images and get a sub-picometer height resolution. I also have here, so 23 images of threefold rotational symmetry. This is now 138 frames averaged. And here we can see this is what's called a vacancy defect in this honeycomb. And you can see this is a five-fold unit, three five-fold units, and then we have these seven-fold units here. And that allows you to take away one TO203 unit. But again, this is now 138 frames average. If we really crank up the contrast on this, you can start to see that actually along this direction and along this direction and along that direction, the atoms are sitting slightly higher. Now, so they are not sitting in their ideal threefold hollow sites, which means they're sitting in elevated positions. And if they're sitting in elevated positions, that's really telling you about the strain field around this defect. So by imaging at this really high with these really high signal to noise ratios, or processing the images to get these high signal to noise ratios, we can image the strain field around a defect of this type. Okay, so I will just conclude then. The main message is really that we get vastly enhanced signal to noise ratios in STM images, and we can do that through image averaging. And routinely, we can get sub-picometer resolution that way, sub-picometer height resolution. And I've shown you an example of the TO203 honeycomb 2x2 monolayer on gold, where we can distinguish between the hexagonal close packed and the FCC and the phase center cubic absorption sites on the gold surface. So structural defects I also showed you can be seen in these films using multiple frame averaging. And the final point I would like to make is that using this approach, it has significantly changed how we do microscopy. So previously, like most people, we used to continuously change imaging parameters to get better images, and then we'd select the best image. But now what we do is we find a stable imaging condition, and we acquire multiple frames at that stable imaging condition and then we actually get much better results than we would have done by changing imaging parameters to get better images. And finally, I'd like to thank people involved in this who were not co-authors, as it were. So these are listed here, and we've also have a close collaboration with Claudine Noguera and Jacek Goniakowski in Paris. And these are the institutions that have funded this work. And of course, thank you and apologies again for the technical problems at the beginning.
Okay, great. Well, first of all, you leave us good time for questions. And second of all, it's really impressive. I mean, seeing a picometer resolution is something we can only dream of.
But no, well, that's my point. You can't only dream of it, because we have a gel microscope. It's not a particularly fancy microscope, but what we do is just take, I don't know, routinely, if you get a decent image, you take 65 of them. You don't just take the single image. So it's not something you can dream of. It's something you can
actually do.
implement.
So I'm just wondering, I know that there have been several works recently where people use machine learning, neural networks and such in order to see things that you don't see, in the images without the processing. Have you compared this to that? And can you say a little bit about the two different approaches?
Yeah, so this is Philip Moriarty, who I know, who's at the University of Nottingham. He does this as well. And their approach is to, as you know, the more STM images you take, or the more AFM images you take, the more likely you are to get a nice result, right? So what they do is they run it overnight, and then they have most of its junk, of course. So they have a neural network to figure out, is it an image that's worth having or not? Should I change the parameters in order to be able to maybe get an image that's worth having? And that will allow you to build up a really nice data set without an operator sitting in front of the computer. So these could work in parallel, actually. If you had an automated way of obtaining the images, and then someone who can and then the image averaging software, actually, I mean, that would be a very good way of combining those two approaches.
Yeah. Okay. Leo, you have a question. Yeah. Thank you. Thank you, Martin.
Thanks for a nice talk. So I would my question is a little bit, what's a good data set of many images? So, and where do you have to be careful not to introduce artifacts by the imaging? For example, I see you sometimes change your scan direction. Do you try to use different tips, or is it better to always use the same tip? And what could be artifacts that you might introduce by the averaging, where you have to take care?
You have to be really careful about making sure that you don't introduce artifacts, because I think, Leo, you're absolutely right. That's one of the big dangers. If you get a tip change, that is not good. So all of the images have to visually look the same, really. Mm-hmm. You can sometimes average images where you have different sizes, but that actually turns out is difficult because the software doesn't like it. So really, at the end of the day, you need at least, well, of the order of at least 10 images where all of the imaging parameters are the same, the tip condition is the same. Visually, if you look at them, you would say these are all the same, right? You know, when you're trying to find the best STM image or the best AFM image, and you're looking through your data set, and then you can't quite decide whether it should be 1, 2, or 7, I don't know. Mm-hmm. If they all look the same, then you can average them fine, no problem. Sometimes because we do quite a lot of elevated temperature work, and sometimes, of course, you get atoms moving around, and you can't immediately see that in the average data. It just looks a bit blurry. Mm-hmm. So you have to be careful about that as well. But you're absolutely right. If you start to impose symmetry conditions, then of course you have to be absolutely sure that you really do have a symmetric image.
Yeah. Oh, thanks. Mm-hmm. Yeah, and 1 picometer, that's really super, no? So that's really yeah.
Sydney, you are muted.
Sorry. Yeah. So Oded Milo from the Hebrew University in Jerusalem We'll be speaking about magnetic-like states and triplet superconductivity induced in a conventional superconductor upon chiral molecules absorption. So, and Odette, I will also give you the 2 minutes, basically after 11 minutes, I'll give you a 2-minute warning so there'll be a little time for questions.
Okay, do you see my slide?
Yes, yes.
Okay. Okay, thanks a lot for the invitation. So as I told you, this is the title of my talk. What I'll try to convince you how non-chiral molecules can, in a sense, become magnetized and induce triplet superconductivity and magnetic-like state in the superconductor, in a conventional superconductor. The work was done in collaboration with the group of Yossi Paltiel and by these excellent students. Now, as you probably, some of you know that in the BCS theory, the Cooper pairs are in the single state and their wave function in K-space is isotropic, what we call S-wave superconductivity. A gap opens in the density of state, a U-shaped gap that was demonstrated very nicely by Norit in her talk, but this is not necessarily so. The triplet, the Cooper pair can be also in a triplet state or a singlet state or even with respect to exchange of spins. Their orbital wave function in K-space can be, again, have odd parity or even parity, and their sign may change sign upon exchanging the time coordinates or remain the same upon exchanging the time coordinates, what we call odd frequency or even frequency superconductivity. And in a sense, any combination that obeys fermionic antisymmetrization is legal here. And one way to detect the order parameter symmetry is Bytonic Spectroscopy. So instead of showing these U-shaped gaps, unconventional or sign-changing superconductivity can exhibit zero bias peak, and also odd frequency S-wave can show a zero bias conductance peak. So by employing this method and also other complementary method, we've shown that the odd frequency singlet P-wave superconductivity can be induced in single layer graphene when it is proximity coupled to a superconductor, for example, by observing this zero bias conductance peak. But now we are also more interested about triplet superconductivity, for example, for applications in superconducting spitonics. Now it is well known now that triplet superconductivity can emerge at the interface between a ferromagnetic and a superconductor. We've also shown it here in my group, but there are of course other ways to do that. But then we have thought that maybe we can employ what is called the current-induced spin selectivity effect or SIS effect that was discovered by Ron Aman in Weizmann Institute. And one thing that we have shown in our group in Hebrew University by Yossi Paltiel, that if you absorb these chiral molecules, alpha helix polyadenine molecules, so they can magnetize the surface of a cobalt, a ferromagnet, by in a direction which it depends on the handedness, either left hand or right-handed, the magnetization direction will be different. So then we ask ourselves, can these chiral molecules also polarize a superconductor? That is, can it induce triplet superconductivity, induce magnetic-like states, or even essentially break a time reversal symmetry? So essentially, we have ample evidence that this is the case. Bytonic spectroscopy measurement, either on niobium or on gold, which is by itself not a superconductor, but it becomes a proximity superconductor by coupling, in this case, to niobium nitride, or in tunneling devices, niobium diselenide exfoliated on pre-patterned electrodes, and also by magnetic measurements, muon spin resonance, rotation, and scanning speed. So starting from the tunneling measurements, so this is very simple. So first of all, these are the typical tunneling spectra that we observe when taking on the pure niobium or on gold. Here, of course, this is a proximity gap, but when absorbing chiral molecules, we see that the tunneling spectra vastly changed. We can see here the appearance of zero bias conductance peaks in all cases embedded in gaps or gap-like structures. So of course, we have a non-BCS behavior and something unconventional. So we found that we can very well fit all the tunneling spectra to a combination of S-wave, which should be there because we begin with a superconductor, which is conventional, and together with a spinful chiral P-wave, given by this expression, which essentially breaks time reversal symmetry. So now we try to get more information and to have even more stable junctions. And we looked at devices where we looked at exfoliated niobium diselenide flakes on tunneling devices, and we studied the dependence of the chiral molecules density and also the dependence on magnetic field and temperature. So this is an optical image of such a flake on pre-patterned electrode. This is what we get in the tunneling measurements before absorption. But in this case, we have dilute absorption. So in this case, we do not find a zero bias conductance peaks. On the other hand, what we find is a series of in-gap peaks, which are symmetrically positioned with respect to a zero bias. And when we apply magnetic field, we see that these states shift apart. Essentially, they act like a zenith effect. So essentially, they behave like magnetic impurities. And these states are very reminiscent of what's called the U-Shiba-Ustinov states, YSR states. When you deposit a magnetic impurity on a superconductor, the exchange energy competes with the pairing energy, breaks the Cooper pair, and in-gap states are induced. And this was found for in many systems, but again, for magnetic impurities, also for magnetic molecules, but our molecules to begin with are not magnetic. And we could also very well reproduce these results using a mean field tight binding Bouguereau-Buttigieg Hamiltonian, where this is the part of the magnetic interaction between the classical spin and the spinor of the Cooper pair. And essentially, what is more striking, I think, and demonstrates more clearly the fact that we are dealing with the magnetic system is that this is theoretic effect. When we look at the data, when we sweep the field from -2 to +2 Tesla, we see that the Shiba bands emerge at some positive bias voltage, a positive magnetic field, I'm sorry. And when sweeping the field from +2 to -2, we see that these Shiba bands, essentially, they are converge at a negative field. And just in passing, I won't go over that. Just recently, we published a theoretical paper that essentially gives the reason why such molecules, again, can become magnetic and induce Shiba states. Then we turn to another junction. Now we have a dense molecules absorption. So this is the flake on a pre-patterned electrodes. In this case, we had good contacts between the electrons and the flake. So we are not in the tunneling regime, but what's called in the Andrea spectroscopy regime. So superconductivity, which emerges at 7.2 K, manifests itself by this dome structure because the conductance increases because of the Andrea reflection. But then at somewhat lower temperature, 5.5, we see the emergence of a very sharp zero bias conductance peak, which is related, we think, to this unconventional superconductivity. Now, when we apply magnetic field, so we see that we can suppress this zero bias conductance peak both for out of plane and in plane magnetic field at fields which are much lower than the critical field, which are 5 Tesla and 15 Tesla for the in plane magnetic field. So we are talking here about a subdominant order parameter, which is induced by these chiral molecules. So the picture that emerges here is that in low temperature absorption, we have discrete YSR states. When we increase the absorption, so we get to a situation where we have what's called a Shiba glass. I mean, they are molecules we saw by Bytonic Spectroscopy. They're not all aligned. We have regions with their alignments in different directions. So this is called a Shiba glass, and the edges of such Shiba glass, so people predict that we have chiral edge states, similar, I guess, to what Nuit has talked about. We did not have seen it yet with STM. But in order to get better information, because up till now the absorption was not in a controlled way, so now we have pattern absorption. So we see that, and we studied, monitored the patterns of the absorption by Kelvin for microscopy. So we see the contrast here. And essentially, this essentially also tells there is some charge transfer upon absorption between the substance and the molecule, which may be related also, according to the theory that I did not show you, to the emergence of a dipolar state, a magnetic state in these molecules. So what we turn next is we joined with Bina Kaliski for Bar-Ilan University, and we performed scanning squid measurements. And essentially, we did see on the edges, we saw reduced magnetization or reduce the diamagnetic response at the edge of the chiral molecules islands. And again, this can be related to weaker superconductivity, chiral edge states. But the next thing that we'll try to do is just to follow what was done in a Bytonic group that was presented by Nuri, and to also to look at with the atomic spectroscopy at possible edge states. The next thing that we turn out to do, we ask ourselves whether these chiral molecules also can induce unconventional Meissner effect. Now, as probably the people in superconductivity know, but maybe not all know, that superconductivity also tells us that there is a perfect demagnetization due to Meissner screening currents. So we try to see if there is also unconventional Meissner effect, penetration depth, and what is the penetration depth of this triplet order parameter, and can we have further evidence for broken time reversal symmetry? So for this, we use the mu and spin rotation relaxation, mu-SR. This was done in collaboration with Angelo Di Bernardo and Zahir Salman. He's from PSI, Paul Scherrer Institute. So we're not going to the details of the mu-SR measurements. I'll just say, but just the geometries, we apply a parallel magnetic field to the surface. The muons are injected with different energies into the niobium, and we can calculate the stopping distribution of these molecules. And when they penetrate, so they start precessing a low frequency due to the magnetic field. So essentially, by emitting the positrons, we can detect this frequency. Now, the accuracy of this method is 0.1 Gauss, and we have
2 minutes.
Okay, we have about a few nanometer spatial resolution. So just when we looked at the data, so of course above TC, so the field inside is equal to the external field. What we see that there is a vast difference between the data acquired at the bare niobium, the niobium with the chiral molecules. These two Gauss difference is very, very meaningful, because again, the resolution is 0.1 Gauss, and the error bars are within these dots here. So the next thing that we done, we did some analytical numerical model where the assumption is these molecules constitute a spin active surface. I will not go into the details of these theoreticals, but the bottom line is that we saw that the energy gap and also magnetization is induced inside the sample. This is due to the triplet induced magnetization in order to get what's called a global field to our data. So we came out with this analytical model where we introduced also this term which called B-spin, which accounts for the induced magnetization by the triplet superconductivity. And we see that you can get good fits to our results, assuming reasonable fitting parameters. And this is probably the last slide I will show. So another way to show that we have a breaking of time reversal symmetry is to see the dependence of the direction of the external field. And essentially, we see that when we apply the magnetic in one direction, we see this profile, and in another direction, we see this profile of the green dots. We see there is a big difference up to about 22 nanometers inside the sample. So this tells us essentially, first of all, we have time reversal symmetry breaking because of the difference due by the directions of the magnetic field. And also we have an estimate of how much this unconventional state penetrate the sample. So just to summarize, at low absorption density, we have induced YSL states. Then we can get unconventional superconductivity shown by STM and also on proximity systems and on a superconductor. And also I did not show you that size matters here in the sense that it's not enough to have chirality, but helicity is important for cysteine, which is also chiral but not helical. We did not see any effect. Of course, we did control measurements. I will not show you. And again, by mu-SR, we found that we have unconventional Meissner effect. And also by looking at the polarization rate, we saw that we have an increase similar to also what Nuri showed in her slide, and which is another evidence for a broken time reversal symmetry in this system. So with that, I would just like to thank so many people that we collaborated, and thank you for your attention. Thank you.
Okay, great. Thanks, Oded. We have time for one very, very quick question, if there is one. If not, I have maybe a quick question. These molecules, they're organic molecules, and they're probably not ordered perfectly, and there's some thermal disorder. I'm just wondering, when you go to the low temperatures, it might be frozen in some disorder. Does the order have any effect of the chiral effect?
Okay, first of all, you're completely true. By STM measurement, we can see that we have regions where they are oriented more or less in the same direction, but other regions where the direction is different. This is why I called it a Shiba glass. Now, if you noticed that we did not, in the YSL state, we did not have only two peaks positioned on both sides, but we have a few peaks. And these may be related to different exchange interactions, which may result from different orientations at different regions. Now, in terms of chirality, so on average, they always have the same component normal to the surface. Now, the question is what we want to study now is also to see what happens if we have mixed in some.
Sorry, I realize this isn't, I'm going to have to cut it, but well, I can talk to you, okay?
Okay.
I'd like to, continue this discussion, but I think we have to move on now. So I'm passing on the chairing of the session to Tatiana, because I'm supposed to be speaking now.
Okay, so
my screen.
Thanks. Do you hear me all? Can you hear me?
Yes, we hear
Okay,
you.
so it's my great pleasure to present our next speaker. It will be Dr. Sidney Cohen from Weizmann Institute, and his title is In Situ Measurements of the Influence of Ice Binding Proteins on Ice Growth by Atomic Force Microscopy in Aqueous Solution. Please, Sidney.
Okay. You see my screen, I hope.
Yes, we see.
So at this point, I don't need to introduce myself, but I would like to acknowledge my coworkers from the Weizmann Institute, Yinon Rudich, and from our colleagues at the agricultural faculty across the street, Ido Braslovsky and his PhD student, Mikhail Chesnitsky. I will point out that this work represents a large part of Mikhail's PhD thesis. Now I need to get rid of my bar here so I can advance the slide. There we go. Okay. So ice-binding proteins, which I'm going to be talking about, they have a number of different roles. They can shape ice crystals. They can suppress the freezing point. On the one hand, promote nucleation. On the other hand, they can inhibit recrystallization. They have certain technological importance, both in food preservation and in health issues when we want to freeze tissues or cells. Furthermore, they help us understand some of these very interesting organisms that can live in very, very cold environments without turning into a block of ice. Now, this work studied two different kinds of antifreeze proteins, which are a subset of ice-binding proteins. One is AFP3, which comes from this ocean pout, which lives in the Arctic. And this is called a moderate antifreeze protein. It binds to the non-basal planes, and it leads to 1.5 degrees freezing point lowering at concentrations of only millimolars. The other species that we studied comes from this freeze-resistant mealworm, and it's called a hyperactive antifreeze protein. It leads to an even larger reduction in freezing point at 1/10 of that concentration. And just to put things in perspective, the colligative freezing point lowering, which we would observe just from what we learned in first-year thermodynamics, is about 3 orders of magnitude lower than this. So this is quite a significant effect. And these proteins, they work by binding to certain crystal phases. So I just want to show you the crystal structures. It's a crystal structure of ice. You see this hexagon with the prismatic faces, which represent the A direction, and the A direction is the fast ice growth direction, and this is capped off by the C direction and the basal plane. So these other planes are less important. Until now, these have been studied by optical microscopy, which has obvious disadvantages in terms of the kind of resolution we might want to get, particularly when we want to look at molecular scale features. So at AFM, besides the advantage of having higher resolution, we can also measure additional properties. We can measure adhesion, we can measure perhaps stiffness of the surface, and that gives us correlative information on the system. Furthermore, we have the opportunity to manipulate molecules with the tip, for instance, grabbing one of these molecules and pulling it off and therefore measuring the binding strength. So there's a lot of possibilities, but it does come with its obstacles. First of all, the AFM has its associated electronics. There's a local heating source, which comes from that electronics. Also, the laser, which is used for detection of deflection of the cantilever, is an infrared laser, and that also can lead to heating. So the other thing is we have to be able to create a very stable growing system. This is a dynamic system. We have to stabilize it in some way so we can clearly see the boundary between the growing ice and the different structures on the ice. And the probe that we're using to measure it also, in principle, presents another surface for nucleation of ice, and we have to keep that from freezing. So this was done in the following way. The very small liquid cell is shown here, and the nose cone of the AFM is dipped into that. There's the cantilever, which approaches this ice surface. This is cooled by two different copper blocks. One is this outer copper block, cooled by a thermoelectric cooler, and the other one is this pyramidal-shaped cone, which is right underneath the measurement point, and that's cooled by a second thermoelectric cooler. The bottom of this cell is covered by a sheet of mica, and a hole of a couple hundred micrometers in diameter is drilled into that. The ice grows through that hole, whereby the tip of this pyramid is held at about -7 to -10 degrees. Now, this allows us to do a couple of things. One is that the ice itself is a relatively good thermal conductor, 3 times better than water, so this serves as a secondary cooling source. Secondly, the thermal gradient that is set up here is such that the perturbation by the heating of the tip is a relatively small perturbation, so the scanning and measuring itself doesn't actually perturb the dynamic system. So let's quickly go to some results. This is something looking at that hyperactive system, and here we see measuring right here at the boundary between the mica, which is here, and the ice. So you can see clearly now we got these steps. These steps range from 1 micron up to maybe 5 microns in height, but on the terraces we see much smaller steps. Since I don't have really a lot of time, I would like to concentrate on one experimental feature which we're able to observe. This is now not with the hyperactive, but with the moderate antifreeze protein, and under the right conditions, we observe these tapered structures. And if you remember the crystal structure, so the sides of these are those prismatic planes, and the tip of the growing tip is the basal plane. So the absorption of the antifreeze protein to these prismatic edges is presumably what pins them, prevents it from expanding in this direction, and leads to that elongated shape. Furthermore, under the right growth conditions, we are able to observe these small pits, which are growing right at the very tip of those growing cones. And if we have time, you can ask me, I can tell you what we think that is caused by. But if we look at a little bit of a larger scale now, we see that those small pits now, they actually take on somewhat of a shape. They take on, again, this kind of a hexagonal shape as you might expect, or a hexagonal pyramid. This was seen optically, of course, at much, much larger scales. We compare this scale bar to this scale bar, but it's all due to the same reason, which is shown schematically here. But before I go to that, I just want to point out another thing which was observed is these are topographic images, but right here we have an adhesion mapping, and we see that this bottom, which we presume to be the basal plane, presents a much higher adhesion than these edges where the protein is bound to. So the tip is binding less strongly to the protein than it is to the areas where there's only ice, bare ice. So this is schematically what is happening. These green dots are the protein. They're binding to these prismatic faces. And so as this crystal grows, this is the basal plane. It is shrinking in area as it gets higher and higher due to this growth structure and the fact that these edges are being pinned. That's in the growth, but of course we have the converse of that if we're looking about the growth of these pits. So to summarize, this was, by the way, the first demonstration of scanning a bulk crystal growing from its own supercooled melt. We've seen the effects of these anti-freeze proteins, how they can lead to different structures on the surface and how they can pin certain faces from growing. And in addition, we saw the functionality of the AFM allows us to look not only at topography, but also at adhesion. And with that, I would like to close, leave a little bit of time for questions, and feel free to contact me by email or otherwise if you would like to do so. Thanks.
Thank you, Sydney. Very nice talk. Do you have any questions, please? If not any, I may ask about this pits, the nature of this. Can you tell us a little bit more, Sydney?
About the nature of what? The pits, yes.
Of the
yes.
pits, please.
Okay. So what is happening when we took those small pits, which were seen for the first time at the edge of those growing tapers, so we think is happening now, this is a dynamic process. So even though that is the basal plane, we're starting to get a little bit of a formation, enough of formation of that prismatic face in order for it to be stabilized by the antifreeze protein, and that allows the pit to develop there. Now, that is the reason, by the way, that these structures are very much dependent on the growth conditions. That was seen under slow growth conditions. Those small pits were not seen under fast growth conditions, where the growing can just engulf very quickly the antifreeze protein, because it's all a dynamic contest between the rate of the binding and the rate of the ice growth.
Okay, thank you. And I'm passing you the chairing back.
Yeah. Okay. Yeah. So I need to remove my. Wait, did I remove my share here? Did I remove my sharing from the screen?
No, not yet.
Not yet. Okay. Let me see. Stop share. Okay. So. Our next talk, Elad Gross from the Hebrew University. You can start putting up your presentation. The title of the talk is What Makes a Catalyst Active? Insights from IR Nano Spectroscopy Measurements on Single Nanoparticles.
Okay. Thank you, Sydney, for the introduction. So there's no family relation to Leo Gross, but we're starting with one Gross and ending with another. So I will briefly introduce you some of the results that we have obtained using IR nanospectroscopy in studying heterogeneous catalysts. So when we talk about the energy challenges of the 21st century, whether it's CO2 fixation, CH4 to methanol, biomass to biofuel, all these challenges are unsolved yet, with the cash reward and impact of billions of dollars. And when we look at heterogeneous catalysts, we can look at them and see that the heart of heterogeneous catalyst is catalytic nanoparticle. And here you can see an example, and you can see that heterogeneous catalysts are actually very heterogeneous. You can see differences structure, differences in the size. And even if we'll focus on a single nanocrystal in this case, we can see that it has various sites. We have terraces, flat areas, and we have steps. We have the metal oxide interface, and all these sites can behave differently and can induce different catalytic reactivity. So the question that we ask in my lab is where, when, and how different sites within single nanoparticle impact the reactivity. And in order to do that, we use IR nanospectroscopy. So IR nanospectroscopy is based on the scattering SNOM. We use synchrotron IR beam with a beam size of 10 micron, focus it on an AFM tip, And then by locally enhancing the IR light, we can extract the localized IR information with a resolution of about 20 nanometer. And in order to detect the reactivity, we also use this kind of a probe molecule, which we make. They are called N-heterocyclic-carbene. They are anchored to the surface of the substrate, and they have this reactive handle, and we can track the reactivity of this handle. So by combining the IR nanospectroscopy setup and the chemical marker, now we have the tools to address a fundamental question in catalysis research and identify where, when, and how chemical reaction evolves on the surface of single nanoparticle. So the idea is that we will take the nanoparticle, here you can see the AFM image, code them with these probe molecules, and then start to expose them to different reaction conditions, and we can track the progression of the reaction. So the first example is oxidation reaction. We put this molecule on platinum nanoparticle. This is a carbene molecule with a hydroxyl group. And then we can track the oxidation. We can track the transformation from OH all the way to aldehyde or acid. So this is the main outcome of this kind of study. So we are looking on two platinum nanoparticle. We can scan and get the IR map across the surface, the center of the nanoparticle and the edge of the nanoparticle. The particles were coated with this OH terminated molecule. And when we look at the center of the nanoparticle, we can see these two humps correlated to these two nanoparticles. We can see the OH vibration, but we don't see any carbonyl feature. Before the measurement, the molecule, the sample was exposed to mild oxidizing conditions. But when we look at the edge of the nanoparticles, we can see, again, the COH vibration, but we can also see the emergence of the carbonyl peak and the changes in the OH vibration. And by looking at this AFM-IR map, along with other characterization, we concluded that we have selectively oxidized the molecule on the edge of the nanoparticle. And on the edge, I'm meaning the edge which has higher corrugation level, higher density of low coordinated surface atoms. So we see higher oxidation yield on the edge versus the more flat center of the nanoparticle. And when we expose the sample to harsher oxidizing condition, we lose this differentiation and we see reactivity across the surface of the nanoparticle. Okay, so when we look at oxidation reaction, we can see the less reactive sites on the more flat area and the more reactive sites on the edges, the more corrugated edges. So this is in oxidation reaction. And then we ask the question, what about hydrogenation reaction? And I want to share with you that in hydrogenation reaction, we're talking about a teamwork. And we can see the interaction between different sites and how different sites influence the reactivity. So when we talk about catalyst, usually we have two different scenarios. Either we're talking about a highly reactive nanoparticle, for example, platinum nanoparticle in hydrogenation reaction, and then we expect to see site independent, or when we have a less reactive site, and then a less reactive metal, and then we put it on an oxide, and then we expect to see high reactivity, but it should be specifically located at the metal oxide interface. And the question that we ask is, what about the other sites on the surface of this metal? We know that the interface is highly reactive, but what about the atoms on the gold surface here? Whether they are active or whether there is any influence of the interface on the reactivity of these metal atoms. So we took this gold nanoparticle, we put it on alumina. We use a different molecule. I will show you a molecule that is said this is a probe for hydrogenation reaction. And we expect to see that the gold oxide interface should be more reactive than the gold surface sites. And we know that, that at the interface, if we have titanium, it's more reactive than silica and alumina. So we start with the metal oxide in which we expect to see the lowest effect of the interface. So again, we have these interface sites and the less reactive sites. And here you can see this is the gold nanoparticle on alumina, and we have a spectrum from the center of the particle, you can see it here, and from the edge, from the interface of the metal and the oxide, and you can see it here. And in both cases, we see two peaks, which are correlated to the symmetric and asymmetric NO vibration. So this molecule has an NO2 groups, neutral group that can be reduced following exposure to reducing condition. So before exposing to any reducing condition, we see the similar spectra on different sites with no indication for reactivity. We expose the sample to various reducing conditions. There is no reactivity at 40, at 80, but when we go all the way to 120 degrees, we see the transformation from neutral to amide. So we lose these two peaks and we gain a single peak, which is correlated to the NH vibration.
Elad, can you try and wrap up soon in a minute or so? Yeah.
So we see no differences in the reactivity. This is what we see on gold on alumina. Similarly, we can go to gold on titania. We can look at the center shown here versus the interface. We see no reactivity at 20, but when we go to 40 degrees C, we see again we see reactivity, but the reactivity is not isolated to the interface, but we see similar activity at the interface and the center of the nanoparticle. So to wrap up, what we see is that there is no influence on, there's no site-dependent reactivity. Although there's influence of the oxide on the overall reactivity, there is no influence of different sites. And by further analysis, we concluded that the molecular mechanism here is hydrogen spillover. So there's hydrogen dissociated at the interface, and then there's spillover to the center of the nanoparticle, and the site on the center are active enough to activate the double bond. And by the diffusion and spillover of hydrogen from the interface to the center, we see hydrogenation on the center of the nanoparticle, throughout the nanoparticle. So this is the teamwork that the active site of the interface facilitate and influence the global performance of the particle. So while in hydrogenation, we see site-independent reactivity due to spillover. In oxidation, there's no spillover, there's site-dependent reactivity. This is actually what I showed you in the first part of this talk. I talked about oxidation reaction, in which we see site-dependent reactivity. In the second part of the talk, I showed you that in hydrogenation reaction, we see site-independent reactivity due to spillover effect. This is also summarized here. And this is the acknowledged slide. Mostly the work here was done by Shachar Deri and with help of other group members. And with that, I would like to wrap up and thank you for your listening.
Okay, very nice, Elad. Again, we have time for one very quick question and one quick answer. So if there's none, then I'll ask. I think this should be a quick one. Is it possible to do these kinds of measurements with a lab system, not with the synchrotron radiation?
Yeah, so now we have a system in my lab. So this is part of this ERC funding. We have a lab-based system that also enables us to do in situ measurements under various reaction conditions.
Okay, thanks a lot. I'm afraid we have to close now the talks, but we do have coming up right now two things. First is a roundtable discussion on atomic scale manufacturing, surface science, and quantum circuits. And right after that, we have the flash presentations for our poster presenters. So I'm going to open now the roundtable discussion. I'll be moderating that, and we have two really good speakers here in the discussion. And of course, we're hoping that those of you that are here will join in the discussion because we do want to have an open discussion. So I'll just give now a very brief, let me get the timing going. Okay, a very brief introduction to this, and then I'll pass it over to the panelists. We know now that we've gotten to a computational world, and there are these very big computers, global data centers. They consume about 1% of the world's energy, about half of this going to the cooling systems. Some of the largest ones, they have about the energy consumption of that which you would have from a small city. And this is just increasing all the time. In the last decade, the quantity of data that's passing through the internet has gone up by an order of magnitude, and you would think this would lead to a huge increase in consumption, but if you look at the figures, it's actually not the case. It hasn't really grown. That's because things have become more efficient. And what we're working for is trying to get to really good efficiency. And just this one example here, if you take the human brain, it works at 1 teraflop, that's floating point operations per second, and consuming only 20 watts. And we compare this to the IBM Roadrunner, which was a supercomputer, which was working at about the same level, but it consumed 5 orders of magnitude greater energy. And for that reason, actually, it was terminated. And people have come to the conclusion that database computing, it really can't be efficient. They looked at other things such as, for instance, neuromorphic computing systems, which are presumed to be much more appropriate for artificial intelligence calculations and the like. And you can see people writing in a lot of places. For instance, recently this appeared in Nano Technology, the roadmap for the hardware and technology for machine learning, which involves all these new kind of computing systems. And I just want to point out a couple of them related to our session. One is using STM to reorganize chlorine atoms, which form a lattice on top of a copper single crystal surface, and using this to write bits. This, I think the writing process, of course, is not so quick. The reading actually can be reasonably quick for this if you use video rate STM, but it does have to be done at 77 degrees Kelvin. Another system is using silicon. Now, silicon has advantages because the industry is used to working with silicon. And this is work done by the group of Robert Wachau in Alberta, where they can form Dangling bonds on the silicon. And these are actually used to form single atom quantum bits. And this is just showing a device, which is these two dangling bond system. It forms actually a device, and you have a 0 and 1 bit systems shown over here. This is just a song which is actually written on the thing, and this is being now commercialized by a company which is working to develop the circuitry which will communicate with these very small atomic systems. So I'm going to now pass this over to our first panelist, Andrea Morello, from the University of New South Wales. They, for a couple of decades already, have been very prominent in developing these computing systems. So, Andrea, please.
Thank you very much, Sydney. Shalom, everyone. Thank you for inviting me here. I'm going to start. I prepared just a couple of quick slides. So interestingly enough, this whole session, which I actually followed all the way through, is really interesting, is mostly about surface techniques and surface science and STM. I'm going to talk about donor spin qubits in silicon, just mention a little bit the things we do and where we're going. And oddly enough, the technique that I use is not a surface science one. It's in fact one that uses standard CMOS technology, such as ion implantation, to place the atoms into the system. So just very briefly, a quick timeline of where we come from. Basically, the field started experimental in 2010 when we were able to do the first single shot spin readout of an electron spin bound to a phosphorus donor. Then in 2012, we made it was actually the first ever qubit in silicon using an electron spin bound to a single atom. Then in 2013, we made a nuclear qubit. And in 2014, we moved to isotopically enriched silicon-28, which is a nuclear spin-free material. And that allows us to get 35 seconds coherence time, which is really phenomenal when you think about it. This is a fully formed silicon CMOS nanoelectronic device connected to high frequency lines and whatnot, and it gets half a minute memory time for quantum information. And then we showed we can control individual atoms in a global magnetic field by distorting the local environment. And then we did single qubit gate fidelity benchmarks, and we got to 99.99%. We can entangle the electron in the nucleus, violate Bell's inequality, prove entanglement. And what we're working on now is 2-qubit logic gates and multi-qubit logic gates to scale up. So the enabling technique for this, which is actually being really revolutionized right now by my colleagues at the University of Melbourne, is this deterministic single ion implantation. I imagine many of you are familiar with the STM technique of placing donors on a silicon surface. That's the top technique that's been developed by my colleague Michelle Simmons here at UNSW. But that method actually is not precise in terms of the number of atoms. They typically result in donor clusters with unknown number of donors, 1, 2, 3, 4, and so on. Whereas we can implant single atoms and have a 99.87% confidence of having placed one and only one atom in the chip. This is a new technique. It's just being demonstrated now, and we are about to introduce it within the rest of the process flow. The state of the art in broadly in silicon quantum computing at the moment is this device here, where we have 2 phosphorus atoms close together, and the 2 phosphorus atoms share a single electron, and with a rotation of the electron, we can do a geometric gate, 2-qubit gate on the nuclei. So we can have an equivalent C0 operation for the nuclei. And so with this, we have basically better than 99% fidelity on 1 qubit, 2 qubit, and state preparation and measurement, which means we are essentially ticking all the boxes almost for clearing the threshold for quantum error correction. Another interesting result is this, we call it the flip-flop qubit, which is an electron nuclear qubit, which can be controlled by electric fields, so by local electric fields. And this is basically where we are. So we have nuclear 2-qubit gate, electron 2-qubit gate, all beyond 99% fidelity. I didn't show you, we have 3-qubit Greenberger, Horn, and Zeilinger maximally entangled states of electrons and nuclei with better than 90% fidelity. We have flip-flop qubits, deterministic single ion implantation, and we're looking at high-spin nuclei. The long-term vision for this kind of work is to really try and integrate the classical silicon CMOS technology, which underpins a $1 trillion industry, with these deterministic single atom implanted dopants in arrays which can be spaced by about 200 nanometers. This is very important because it means that we have the space to put interconnects and readout devices within the device. So this is broadly where we are. I'm looking forward to having a conversation about what people think in terms of how this blends with the local interests and the bigger picture. So ask me any question.
Okay, thanks, Andrea. I think what we'll do is we'll have now our second panelist, Michael Stern from Bar-Ilan University, say his few words, and then we'll open to discussion.
Yes.
Yeah, Michael.
So good morning, good afternoon. Yes, I will also try to show you a very small presentation, okay, to introduce superconducting qubits in a more general way. So I'm going to share my screen. Yes. So I think that our lab in Bar-Ilan is trying to couple superconducting circuits with spin. So in order to couple spin together. So we are very close to what Andreas is doing, but let's say in a different manner. So typically what you want when you want to build a quantum computer, you want to build a qubit register. And in order to build your quantum computer, you need several tasks. You need to have a qubit with several properties, the so-called DiVincenzo criteria. So what you need to be able to initialize your calculation. You need to be able to start from 0. You need to be able to manipulate your qubit. Okay, so the single qubit gate that Andreas has shown you. You need to be able to read out the qubit. You need to be able to entangle 2 qubits in order to make this 2 qubit gates, these C0 gates. And all of this needs to be done in a time which is long enough short enough in front of the decoherence time of the qubit. So this defines, in fact, the relation between the decoherence and the time for entanglement defines the fidelity, for example, of a signal gate. So, so what we are working as a basis is a superconducting circuit. So a simple example of superconducting circuit is, for example, take a capacitor in here, which is connected to this inductor. So if you look at this, it's an LC circuit, but put dimension, for example, typically 2 millimeters, you will get something which is in the range of a few gigahertz. And if you add to this superconductivity, you have a way to get rid of internal degrees of freedom and loss of energy to internal degrees of freedom, especially electrons. And by that way, this system is in a way isolated from its environment and should behave quantum mechanically. So there is a direct analogy between this LC oscillator and an harmonic oscillator. Okay, I will skip. But basically, you get an harmonic oscillator, so you get energy levels. Okay, and the question is, when does this system behave quantum mechanically? In order for the system to behave quantum mechanically, you need that the distance between the energy levels to be very big in front of the temperature. So this requires to be in a temperature range much below than 250 millikelvin. The second condition is that you never have discrete levels. You have always a band, and you need that this band would be small in front of the distance between the levels, or if you prefer, you need to have a high Q, high quality factor resonator. So if you have these two conditions, your system should behave quantum mechanically. But this is not enough, because in order to speak about qubit, what you need is also to have some kind of nonlinearity. And there is this wonder of nature, which is the so-called Josephson junction, which gives us this nonlinearity without having a price to pay in terms of it's also non-dissipative. So we don't have a price to pay in terms of dissipation. It's a very rare system in nature that is at the same time nonlinear and non-dissipative. Okay, so this sandwich between superconductor, insulator, superconductor, which you see here, TEM image, is a very nice system and allows us to have this anharmonic potential and to consider a qubit, to transform our harmonic resonator into a qubit. So in this, when looking at now at the parameters of this qubit,
Michael, sorry, can you kind of cut? So we have a little time for discussion. We only have about 5 minutes left from the whole session. So
okay, so I will try to make the things quick. So basically, what you have is you have two parameters. You have the so-called Josephson energy and you have the capacitive energy. According to the ratio between these two parameters, you define a kind of zoology of the qubits. You can be in a Cooper pair box regime, you can be in a transband regime, you can be in a flux qubit regime, or in a fluxonion regime. So I'm going to speak only about a few possibilities. The transband qubit, because it's the most popular today, consists of a big interdigitated capacitor, one in front of the other. In the middle, you have a wire here with a Josephson junction. This qubit is a very nice qubit, except that it's, in particular, it is very close to be a resonator. And as a consequence, this qubit will have a very small anharmonicity, which limits our ability to, which gives some limitation in terms of frequency crowding, in terms of also control and fidelity. So basically, what people found is that in order to improve the coherence time of transband, it's better to put them into three-dimensional cavities. But you see immediately that these qubits become very big. They are of the order of 50 millimeter size. More recently, there is this article from the Princeton group, which has shown that it's possible to have a very good coherence time and especially very good T1 by using what they call the tantalum transband. Okay, another alternative is the flux qubit, which we are working on. In the flux qubit, we have 4 junctions. It's a much more complex qubit, but the advantage of the flux qubit in front of the transmon qubit is exactly the fact that when you are working with a flux qubit, you are working with a true 2-level system. It's almost a spin, if you want. The other levels are very, very far. So it allows us to have gate duration which are much more smaller than what can be done with a transmon, and allows us to reach fidelities in the range of 99.9%. So basically, the advantage of the superconducting qubits, according to Divinchenzo criteria, are the following. We have initialization, manipulation, readout, entanglement, but the problem is low decoherence. On the other hand, as I think Andrea has shown you, the advantage of spin qubits are initialization, manipulation, readout is possible. Low decoherence is, of course, extremely good, but in terms of entanglement, it's quite an operation. So the question is, how do you build them?
So, Michael, maybe sorry, maybe we can. Yes, start it now, and we just only have now. I'm sorry, I'm being so strict, but I need to.
Yeah, no, you're right. Yeah. Completely fine.
So first of all, thanks you to both of you for giving us an update on where this really fascinating field is at right now. Is there any input of discussion from the audience? So I had a question for both of you. You both talk about fidelity and you give numbers, but I have no idea what fidelity is needed in order to make these systems realistic in terms of computing.
Okay, it's a very good question, Sidney. In fact, the question of fidelity comes when you want to scale up. Okay, so with a fidelity in the range of 98–99%, you can begin to think of correcting errors, because a quantum computer will always do errors. Okay, so you have to correct them. But in order to correct them, you have to, error correction is always working with, you multiply the number of qubits that are storing the information. It's always like that. So in order to have a scheme which is which is not extremely difficult to implement, you need to have very high fidelities. So fidelity means the ratio between the time you need to apply a gate and the coherence time. And this time.
Yeah, so Michael, if I may just suggest, I'm just sharing this slide. I went through it, but in the interest of time, I kind of flew over it. Basically, this is the slide that answers the question. So in order to have a functional fault-tolerant quantum computer, there's various schemes, but the most popular one requires 99.4% fidelity on everything, on 1 qubit, 2 qubit, and state preparation and fidelity. So this is basically where I was trying to show where we stand with respect to that benchmark, because that is essentially the level you need to reach. So there's a number of physical systems that are at this level, and just now, literally in 2021, spins in silicon have reached this level.
Okay, Leo, you had a comment.
Yeah, I had a question. So, I mean, both of you work on implementing quantum computers on single atomic scale, nitrogen vacancies or phosphorus dopants. And right now we already have these systems that you can access even through the internet based on charged superconducting qubits. So what's in a simple picture, what's the big advantage for going to single atom sized qubits compared to these larger systems?
Size. So if you look at the number of physical qubits that you need to perform, let me call it useful calculations. So useful calculation require hundreds of logical qubits, so error corrected qubits. And every logical qubit at realistic physical error rates will be composed of a few thousand physical qubits. So you're closely coming to numbers of about millions of physical qubits in order to have an actually useful quantum computer that does things that classical computers cannot do reliably. So, the kind of, IBM, Google, Transmon systems that are ahead of the game at this moment, there's no question, have physical qubit size that are, a fraction of a millimeter. So the area necessary to place millions of qubits becomes problematic. And because these are essentially microwave resonators, the microwave hygiene implied in having, centimeters, tens of centimeter size chips becomes complicated. What people are doing right now is trying to go in 3 dimensions. There's a lot of work in trying to making superconducting interconnects between stacked chips. So instead of going bigger area, you go up that way. So there's people, of course, not giving up, but the main motivation is really scale. And also, again, as I was trying to show in the last slide of my talk, with atomic system integrated in CMOS devices, we are looking at a pitch that is of order 200 nanometers, which includes the control and readout lines and readout devices, which means if you do the number, is 25 million physical qubits per square millimeters. So that starts to be interesting, right? So you have tens of millions of physical qubits in a small chip, including readout and control lines. So that's it's hard, it's not easy, okay? But that is the kind of goal that's worth going for.
Okay, well, I hate to end this. It's really been great, but we have to move on. We're already way beyond schedule. We're moving on now to the flash session. There are 5 one-minute flash presentations. You know who you are, you presenters. Your slides are all here. Each of you have 1 minute, and we'll go from slide to slide. So go ahead. Abhijit, you can unmute yourself and present your slide. Are you there?
Yes, sir. Yes,
yeah, go ahead. Please start.
So, okay. Good evening to all of you. So, my name is Abhijit Das, and I'm a research scholar in the Department of Physics, Rajiv Gandhi University. So, today I'll be talking about one of my works, that is the consequence of PV doping mediated surface morphology on the conductivity of series thin films. So, and we have studied it in the framework of fractal geometry. So, surface morphology, dynamics, and conductivity of lead-doped cadmium sulfide were studied using stereometric and fractal analysis. We have computed the height parameters, and it shows a non-linear trend with increasing doping concentration on the surface roughness of CDS thin films. So, and based on the stereometric analysis, we have observed that there is an influence of PV doping on the microtexture porosity and elastic deformations and dominance of lower spatial frequencies in the surface of cadmium sulfide thin films. Now, in the framework of fractal geometry, the observed roughness in the thin film surfaces from height parameters were validated from the local surface slopes. And we have also observed that there is an interdependency between the self-affine behavior of PV doped CDS thin films with the doping concentration. Further, we have used advanced fractal geometric techniques to study the topographic uniformity and degree of surface population.
Okay, sorry, time's up. We have to move on. Okay, next, Michelle.
Hey, good afternoon. My name is Michelle Ackerman, and I will talk to you about charging amorphous solid water films by neon ions characterized by contact potential difference measurements. All of these experiments are conducted under ultra high vacuum conditions, temperature range of 35 to 120 Kelvin. The films of amorphous solid water are grown on a ruthenium substrate and are subsequently charged with neon ions, which leave a positive charge on the film surface. The voltage developed across the film is measured by a Kelvin probe, which measures the contact potential difference between an inert Kelvin probe electrode and the sample containing the film. The charging leads to the development of a stable nanocapacitor, which follows parallel plate capacitor physics and generates strong electric fields within the film. The charges themselves are trapped in defect sites slightly below the film surface. The charge stability and strength are highly temperature dependent, and we plan to use this model system in order to study chemical reactions under the influence of electric fields.
Thank you. Great. Okay. Rita.
Thank you. Good afternoon. My name is Margarita Shepelenko. I'm from the Weizmann Institute, and my poster summarizes computational study on cholesterol monohydrate molecular crystal, which is of relevance to atherosclerosis. We obtained detailed structures of the triclinic and monoclinic polymorphs, revealing an ice-like hydrogen bonded network in the monoclinic form, which is different from the hydrogen bonding motif of the triclinic. The triclinic form is the most stable of the two, but only marginal so. By contrast, as a single cholesterol bilayer in hydrated membrane, the monoclinic form is always obtained, and we address this computationally. Finally, we suggest that pathological nucleation of cholesterol monohydrate in atherosclerosis can be induced by cholesterol palmitate ester, which packs in the monoclinic form, and this via pentaxyl fit at the interface. And you are welcome.
Okay, thank you. Yeah, Ramesh.
Hi, today I'm going to talk about a protein-based freestanding proton-conducting transparent elastomer for large-scale sensing application. So what I've done here, we use a naturally abundant protein to make a freestanding transparent and conductive elastomer, which has a stretchability of around 5 times and has a Young modulus of 12 megapascal. And because the raw material is very cheap, it has a very low cost, 0.01 USD per centimeter square. It's biodegradable and non-cytotoxic, and it has a proton conductivity of around 5.3 millisiemens per centimeter. And we have used this material to record electrophysiological signal, and it can record very successfully the electrophysiological signal. Finally, being protein-based nature and its biodegradability, its stretchability, and it is also transparent in the visible region. It has a high potential in many bioelectronic devices and other applications.
Okay, very good. Thank you. And our last flash presentation, Lev.
Hi, I'm Lev. In our research, we demonstrate how argon annealing enhances the homogeneity of VACNT nanocomposites. VACNT is carbon nanotubes that are vertically aligned, conserving their anisotropic properties. It's a very gainful to coat them with another phase, fabricating nanocomposite materials with highly anisotropic properties. VACNT restricts the methods of post-processing, as wet methods are destructive to the alignment, leaving us only gas-based methods, such as atomic layer deposition for the coating step. In a recently published article, we demonstrate a significant variation in accessibility throughout the VACNT architecture, which hinders the homogeneity of all processes performed onto VACNT. Previously, coating suffocation depth kept at 340 microns, and using argon annealing, we have managed to reach 0.7 and even 1.5 millimeters. And in this project, we showed the chemical, morphological, and structural effect of the argon annealing on the VACNT.
Great, okay. So I would like to thank all of our speakers, all of our participants this morning. It's really been a fascinating session. I'm sorry that we had to cut it off so short. I would recommend for all of us now to move on back to the main session. We'll come out of this session. There's a lot more exciting things going on. There's the posters, there's the exhibition, of course, the afternoon sessions and the afternoon plenaries. So thank you again to everyone, and we'll see you. Bye.